Welcome to Vehicle Engineering Part 3. In our previous video, we discussed how the clutch works. In this video, we will focus on how a manual transmission works. A manual transmission, also known as a stick shift or standard transmission, is a type of gearbox used in vehicles to transfer power from the engine to the wheels. Unlike automatic transmissions, manual transmissions require the driver to manually engage and disengage gears using a gear stick and clutch pedal. A typical manual transmission consists of several key components. 1. Gearbox. The gearbox contains the gears that transmit power from the engine to the wheels. In a 5-speed manual transmission, there are typically 5 forward gears and 1 reverse gear. 2. Clutch. The clutch connects and disconnects the engine from the transmission. When the clutch pedal is depressed, the clutch disengages, allowing the driver to change gears. When the clutch pedal is released, the clutch engages, transmitting power from the engine to the transmission. 3. Gear selector. The gear selector or gear stick is used by the driver to select the desired gear. Moving the gear selector into different positions engages different gears in the transmission. When the engine is running and the clutch pedal is engaged, power is transmitted from the engine to the input shaft of the transmission. The input shaft rotates at the same speed as the engine. When the driver selects a gear by moving the gear selector, the corresponding gear on the output shaft of the transmission is engaged. The output shaft is connected to the wheels of the vehicle, so when a gear is engaged, power is transmitted from the transmission to the wheels through a differential, propelling the vehicle forward or backward. The gear ratio determines the speed and torque output of the transmission. Lower gears provide more torque, while higher gears provide higher speeds and fuel efficiency. That is just a summary of how a manual transmission works. To get a better understanding, let us strip the bell housing. The input shaft connects to the engine through the clutch. The counter shaft, constantly meshed with the input shaft, receives its power directly from the engine whenever the clutch is engaged. Gears of different sizes suitable to the corresponding output gear are fixed to the counter shaft, and they spin as a unit. The output shaft connects the counter shaft to the drive shaft and eventually to the wheels through the differential. Just like the counter shaft, the output shaft also has gears affixed to it. However, these gears are mounted on bearings, and in as much as they are constantly spinning thanks to being driven by the counter shaft, they don't actually turn the output shaft, at least not yet anyway. The big question remains: if the gears affixed to the output shaft are spinning freely, how do they drive the wheels? Well, this is where the locking collars come in. The locking collars rotate with the output shaft and can shift or slide back and forth to engage one of the gears on the output shaft. In neutral with no gear selected and the clutch released, the input shaft, the counter shaft, and the output shaft gears continue spinning, but the output shaft does not move because none of the locking collars are engaged. Along with the locking collar are the spline sections mounted on the output shaft parallel to the locking collar. The synchronizer hub is fitted over the spline sections. The splines lock the synchronizer hub so that it also rotates along with the gear when engaged. The synchronizer system consists of 3 parts, namely synchronizer hub, synchronizer sleeve, and synchronizer blocker ring. The synchronizer hub is the inner ring mounted over the spline section, and the synchronizer sleeve is the outer ring. The outer surface of the hub and the inner surface of the sleeve are both splined, which interlocks the 2 parts. The sleeve can move horizontally on the splines of the hub. When the output shaft rotates, the synchronizer system rotates along with it. Synchronizer blocker ring, which is the outermost part, is fitted at both ends in the synchronizer system. It has straight teeth at the edges. It rotates along with the sleeve and the hub. When a gear is selected, the blocker ring rubs with the gear and locks with the straight teeth / spur gear present at the outer edge of the gear. The locking action increases the friction between the gear and the sleeve, hence matching their speed before the gear is engaged. The synchronizer is placed between pair of gears, for instance, between gear 1 and 2, gear 3 and 4, and the shift fork is connected to it. When a gear is engaged or disengaged, the shift fork moves the synchronizer back and forth. Helical gears, namely input gear, counter gear, and output gear, are mounted on the input shaft, counter shaft, and the output shaft, respectively. These gears are preferred since the gear teeth are at a certain angle called the helical cut. The spur gears with straight cut teeth are used on the edge of the helical gears and rotate along with it. It is also called dog's teeth. The straight cut teeth present in it are used to lock on to the synchronizer blocker ring, which ultimately locks the sleeve and allows it to rotate at the same speed as the gear after syncing the speed. Shift forks are connected to the synchronizers between gears. Each shift fork and synchronizer is used to engage or disengage a pair of gears. It moves the synchronizer back and forth between the gears. It is linked to the shift rod, which moves the shift fork when a driver uses the gear shifter. Selecting first gear. The driver depresses the clutch, disengaging the input shaft. Using the shift lever, the driver selects first gear, and the shift rod moves the shift fork to connect the 1 Sane 2 and synchronizer with first gear, locking it to the output shaft. Now, when the clutch is released, engaging the input shaft, the output shaft turns because first gear is locked to the output shaft by the synchronizer. As the driver speeds up, selecting second gear simply involves repeating the process, but moving the shift lever to second gear. The shift rod moves the shift fork to disengage first gear and engage second gear. Releasing the clutch engages the input shaft again, this time routing power through second gear. Changing to third gear involves using a second shift rod, shift fork, and synchronizer, this one between third and fourth gears. The idler gear is used when reversing the car. The idler gear is used to reverse the direction of the output shaft. When engaged, it is placed between the counter gear and output gear. This makes the output gear rotate in the opposite direction. The gear ratio decides the speed at which the meshed gears can produce. For example, if both the gears are of the same size, the gear ratio is 1:1. But if the driven gear is double the size of driver gear, it provides a ratio of 2:1. Lower gears produce more torque and low speed. They are essential when driving uphill. Higher gears produce more speed at low torque. They are useful when driving of a flat surface because you do not require more torque. Grasp this for today and let us meet again in the next video.